Hi, everyone. Welcome to this session on Astronomy 101. Today, we are in the week before, we still have two more this week and next week of instruction. And then the week after is for the final exam, which is going to be midterm 3. So this is basically the plan for this class. I hope that you guys are going through Canvas and making sure that you're doing all of your assignments. We have a review actually that's going to be available this week for your midterm, and it should help you prepare for the midterm, which is again on, let me make sure I have the correct date in here. I don't want to give you something that is not correct. Let me check. So the midterm review actually is going to be available in week 14, but week 14 is actually open now. So both of week 13 and 14 are open right now. So you shouldn't really have any problems in terms of your review. If you do, please let me know. The actual midterm is actually planned for December 14th, which is a Wednesday. So December 14th, which is a Wednesday, that's when your actual midterm is planned. So hopefully you guys will have time to go through it. It's no different than most of what we did so far. So it should not be hard. There is also important items in here in terms of the discussions. They are not graded right now for week 13 and week 14. But in terms of quizzes, we still have actually one quiz from the week before, quiz 5, and we still also have quiz 4 and quiz 6, and they're all due by December 9th, which is next Friday, not this Friday, but the Friday after. So I was just looking at the Canvas, the way that I have it set up. We have quite a few units to cover actually, so I'm going to get through them at least hopefully today. But it's still your responsibility actually to do the reading and making sure that you're preparing everything you're supposed to be preparing to meet all of the requirements for this class. If you have any questions, if you think that something is probably not clear or something you guys you need help with, please reach out to me and we should be able to do that. We have actually for those sitting in astronomy lab, we have a lab for astronomy section 1 tomorrow, and we still have another section also for section 2, which is on Thursday. We still also have lab next week for section 1, which is Tuesday of next week, and also Thursday of next week for section 2. So if you're sitting in those labs, you're aware of these, and if not, then basically you're excused from this announcement. For those sitting in astronomy lab, as a matter of fact, next week is not going to be in the regular class. I just remembered that we had planned to go to the planetarium, and that's going to be on Wednesday. Anyway, so if you are interested in going to the planetarium, although you are sitting in Astronomy 120, which is the regular lecture, you're more than welcome to attend. Please let me know, and I will be more than happy to take your name and also add you to the people who are going to join us for the astronomy, for the lab, for the planetarium, which is going to be on Wednesday, December 7th. So that's the whole plan. There will be no more labs after this one. So on the finals week, there are no labs. So that's basically how the college is structured, the instruction in here. Okay. As I said, there are quite a few topics to be covered. I'm going to try to cover about half of them this week. We're still dealing with the stars. And we're going to get into the galaxies and try to understand more of the rest of the topics that need to be covered. You have to do the reading. You cannot rely on these lectures, and you cannot rely on the discussions that we have in here. And there are some videos that I post, I know, in the discussion sessions and things like that. Please follow the instructions in there when it tells you you're supposed to do reading on this and that unit, to make sure you do those. Otherwise, we're going to struggle with the exams. Let me share with you the screen. And the units we're going to cover today are 3 units, actually, unit 60, 62, and 63. So make sure I have those correct, okay? Hold on. Let me make sure I follow the lineup for the way that we have them posted. Actually, it's 60, 62, and 63. Yes, that's the units. Yes, 65, 67, and 68. We're going to leave them for for Wednesday. Okay, so I'm going to share Unit 60. And Unit 60 deals basically with the phases through which the stars pass through. Namely, a star, first of all, has to go through a pre-star stage, namely protostar, then through its main life, which is usually in the main sequence stage, which puts it on that diagonal in the HR diagram, if you guys remember. And then after that, it starts to migrate outside of the HR diagram, where it goes through a giant stage, supergiant stage, depending on the type of the star. And that could end up in one of basically two possibilities, either in a white dwarf for low massive stars like the sun, or for an explosion that is a nova. We're going to try to classify novas later on into different kinds of types of supernovae, say. And that can result in actually one of two products, either a neutron star for the supermassive stars, but not big enough. They have to exceed a certain threshold, which is about 8 solar masses, or a black hole. So that's basically, in a nutshell, how a star really evolved through its life cycle. Okay, and we'll try to understand that and see how we can sketch the evolution through the HR diagram. So again, stars basically go through their life cycle just like humans do. And how do we know that? It's very, very important that we understand the process, because sometimes we tend to talk like this and we think that maybe somebody has observed a star go through its life cycle, namely being born, then after that goes through its main sequence age, and then go through its supergiant phase and explosion or white dwarf. This is not possible. We have been observing the skies, even the earliest human that we can think of that looked at the skies, they're only a few thousand years ago. And the life cycle of a star spans millions, billions, sometimes trillions of years. Way after we humans basically go extinct from this planet, and way after the entire planet basically ends, stars will still continue to shine, okay? And they're going through their life cycle extremely, extremely slow compared to our lifespan. So how do we know that? How do we know basically what we know about the stars? One way of doing that is by looking at the sky and scanning the sky, and basically seeing different stars at different levels, different stages of their life. We will see stars that are being formed. We see stars that are basically about to go into their stage of becoming a star. Stars like the sun that are in the middle of their life, basically they are born some time ago, billions of years ago for that matter, and still have billions of years to go. And we see stars that are in their red giant stage that have exhausted their main sequence level, and now they are actually toward the end of their life. And we see supernovae, suggesting that stars already went extinct, like the famous one that happened in 1987 that was observed live actually by modern technology. It happened in the Magellanic Cloud, which is a satellite cloud to our own satellite galaxy, to our own galaxy. And we observed them in the ancient times, and the word nova actually was constructed based on the observation of a bright star that appears to be so bright in the night sky and stays for several days that people thought that that's how stars were born. It actually turns out to be the other way around. That's how stars end, actually. Okay, and that's basically where the word nova is coming from, Latin, I think, which means new. Okay. So, but it turns out that's actually the opposite. It's the end, not the beginning of the star. So we observe all of this and we make a model, but hey, this looks like it's young, depending on its composition also in terms of spectral analysis. We will see that this has so much content, this one has less content, and so on and so forth in terms of this material and that material. This is light on in terms of the heavier elements, and this one is rich on the heavier elements, and so on and so forth. That's how we determine, based on the processes of what we think is happening. We model that on a computer, and it looks like it's working. So you take a star, you give it this much basically composition in terms of hydrogen, helium, and some heavier elements, and this much content, and you will see it evolve on the computer. Based on that, we will draw a comparison. It looks like the model is working, and that's true. And this is how this is how we came to this determination. It's not, as I said, somebody actually observed the stars and determined that they go through their life cycle, because there is not enough life, time here on Earth to even observe one star. Even the shortest lived stars, let alone the longest lived stars, that will for sure will outlive anything that we know of. Like, for example, the brown dwarf, that their lives can go into trillions, possibly even more, quadrillions of years. So it's a ridiculous number of time that you can even imagine. So that's basically one point. It's like, for example, and this analogy is textbook analogy, it's like somebody, an alien, for example, flying through Earth, zooming at an extreme high speed, takes a picture of humans on Earth. Obviously, that person is not going to take a video. It doesn't have the time when he go through basically a fraction of a second looking at Earth. So he takes a picture of the Earth and looks at the humans, and he finds humans at the early stages. Probably humans, basically women pregnant, indicating that this is where probably the birth is, then babies, and then he sees in the picture there are some teenagers, and in the picture there are some adults, and in the picture there are some old age people, and in the picture there are some cemeteries. So he can conclude based on this picture, only one picture, that this is the lifespan of people. This is how they start from the conception all the way to death. So that's basically what we're dealing with. This is basically the analogy that we're dealing with in here. So we take pictures, even if we look at the sky for a long, long time, it's not long enough for a star to evolve. So it's very important to understand this idea that this is basically how we look at stars, and stars go through their life cycle just like any other organism, basically. And just to remind you guys that the star basically has when it's born, it's brought together by a force of gravity, and the force of gravity puts it closer and closer. That gas and dust that exists, that spends light years, as a matter of fact. For some stars, like, for example, the low massive stars, few light years. For the supermassive stars, even several light years. But then as that gas gets together and comes together, that increased pressure will lead to a higher temperature, and that heat will ignite the nuclear fusion that prevents further collapse of the gas. Otherwise, the gas will continue until it basically becomes in the dot. So that's basically what keeps the star together. And then when it runs out of fuel, basically the nuclear fuel, which is mainly hydrogen in the core, and then after that, when it gets hot enough, it starts to fuse heavier and heavier elements, including helium and carbon and oxygen and magnesium and whatever other elements in the periodic table, until it reaches some point where it's either going to end up either at a white dwarf, like for the case of a small star, or low mass stars, like for example the sun, or is going to turn into a neutron star, that the compression becomes so big that the protons basically and the electrons, they're forced to fuse together and form neutrons, hence the word neutron star. And even for even bigger stars, this process cannot be even sustained, because at that point, there is something called neutron degeneracy, which prevents further collapse from the neutron star, stays intact. But if the star is massive enough, even that degeneracy, even that repulsion due to this something called exclusion principle of Pauli, that's going to be overcome, and the star will collapse even further to a black hole. The case of the white dwarfs, which are beasts on their own, I mean, we're talking about these densities that are ridiculous. It's actually the electron degeneracy that prevents further collapse of the white dwarf. There is not enough material in there. There is not enough material to compress further to overcome it. So in this case, electrons cannot occupy the same energy level, so they will repel each other. Just like, for example, you take a bunch of billiard board, for example, or a bunch of marbles, for example, you try to squeeze them to one another. At some point, they will not allow further squeeze. When they are spread apart, that's fine, they can exist. But when you try to clump them together, they will prevent further collapse. But if the force of compression is big enough, that can crush them further. So this is basically what the electron degeneracy and the neutron degeneracies are. And this degeneracy is true for all elementary particles. It's not just, as least, I said it probably too hastily. It's true for the common type of elementary particles, namely proton, neutron, and electrons, okay? And if the force is big enough, where the electrons now are forced to get closer and closer, at some point they will fuse with the protons and form neutrons. And when they do that, then you have a bunch of neutrons that are floating everywhere. But the neutrons now cannot go into one another. They actually will repel each other at those extreme close distances because they cannot occupy the same energy levels. And this is known as the Pauli exclusion principle. And here it's called the degeneracy, okay? Whether it's for electrons, or in this case, neutrons, because we don't care about protons, because protons are a middle stage that's going to be basically immediately basically overcome. So for the case of the white dwarfs, it's actually the electron degeneracy that presents further collapse. For the case of neutron stars, you actually need stronger forces than the electron degeneracy, namely the neutron degeneracy that prevents further collapse. And if you have too much mass, then even that is going to be overcome and you end up in a black hole, okay, where there is basically no force to stop it from further collapse. So that's basically in a nutshell what's going on. So for the case of a low mass star, so you start with gas and dust, interstellar clouds, molecular clouds actually, that starts to clump together due to the force of gravity. Okay. And starts from few light years, as I was saying before, and it starts to come together. So little by little, and it takes millions of years, about 1 million years or so, depending on the material that is clumping together, until at some point become too close from each other. The pressure is so high, and the nuclear reaction starts. Now, because it's a low mass star, the process is kind of slow, okay, getting it together, because you really need to gather a lot of spread materials in here trying to make them together. And the process expedites later because a bigger mass will attract more material than a small mass. So in the beginning, you have small masses, so the attraction is kind of slow. But then as the clump starts to grow, then in this case, your attraction is bigger. Because remember, the force of gravity is proportional to the mass times the other mass that you're trying to bring in. So this is the mass, this is the other mass. As this one gets bigger and bigger, it's going to attract more and more. That's basically a nutshell, divided by the distance squared, by the way. The further they are, the weaker the force is. Times the constant g. Remember, this is the Newton's universal law of attraction. So in this case, you're getting material closer and closer. And the problem with that is because of the increased pressure, that will result actually in increased temperature. That actually will result in another thing. And here the temperature increases until at that point, at some point, the temperature is a few million kelvins. And that is going to trigger a nuclear reaction inside the core that is going to fuse hydrogen. Remember hydrogen chain, namely 4 protons will meet together to give you helium atom plus 2 neutrinos plus energy. That energy is now what is going to prevent further collapse, because now you're pushing away with the energy. Force of gravity is trying to collapse the material, and you reach a balance, okay? You reach a balance, and then now the star really at its zenith stage, okay? 0 age main sequence star. Basically, it started its life, okay? That's it. That time, the whole size shrinks from a few light years to about 200 astronomical units. 200 astronomical units is a large distance. Remember, the furthest planet that we know of, or at least dwarf planet that was at least known at some point, was actually Pluto. And Pluto is about only 40 light years or 30 light years from, 40 light years from the sun. So 40 is about 5 times further away. That's basically the size of the solar system. Okay, this is an average star similar to the solar system. Obviously, because of conservation of momentum, the disk flattens, but then there are jets that is going to emanate from both the north and the south, in this case, from where it's spinning. So in this case, those are the bipolar outflows. It's going to go through its main sequence stage, and this is where it's going to spend most of its life, until at some point it will going to run out of hydrogen in its core, and in that case, there is nothing to prevent the core from further collapse. So it's going to shrink. And as it does, the temperature increases. Again, remember, you lose potential energy, you gain kinetic energy. Kinetic energy is heat, it's temperature. So the temperature increases. Now, that is going to cause the fusion in the outer shell. And that heat that is generated will make the star now even bigger. When it gets bigger, now it's the same energy, but it's spread throughout a bigger area. So when it comes down to the outer air, it's going to cool down, and the star appears reddish in colors. Hence, it's a red giant. Well, at that point, at some point, it's going to run out of energy. So what's going to happen in this case is going to, again, shrink due to the force of gravity, but then that will cause actually helium surging to fuse, and that is going to prevent it from further collapse. And when it turns out of that, it's going to even expand when it's going to go through a different red stage, in this case, second red stage, where it's going to actually start fusing more and more of the helium. At some point in the process, it will run out of completely fuel, because it's going to start to try to fuse heavier and heavier elements, but it's not really going to pass carbon in this case. This is a low mass star. At that point, it's going to collapse, and the material that is outside in there is going to escape in a planetary nebula that is going to go and seed the next generation stars. And the core will collapse into a white dwarf. A white dwarf is the size of the Earth. So this is about the size of the Earth. Remember, we started with the size of the sun, which is about 100 times bigger than that of the Earth. Now we're down to about the 100th of that, which is the size of the Earth. So a white dwarf is about the size of the Earth in terms of size, but it's a beast on its own. And as I was saying, it's only prevented from further collapse because the electrons do not want to be on the same energy level. They don't want to be in the same place. So that they resist further collapse. This is an extremely dense material, extremely dangerous, basically, situation. When it gets in, because of the collapse, the temperature increases, and it's going to be in the thousands of Kelvin. And these are beasts on their own. These are animals that you don't want to be near them. So those are the remnants of normal low mass stars, just like the sun. Obviously, the planetary nebula is rich now in heavier elements, in addition to the hydrogen and helium, that is going to seed the next generation stars. And the process continues now until we run out of completely materials. It's so dispersed that it does not coalesce anymore. So that is basically how the low mass star evolved. In a similar fashion, a high mass star evolved slightly at a different pace. First of all, faster. It starts with several light years as opposed to a few light years of material that gather. So it starts with more materials. And because of that, the material starts to coalesce in the same similar process, but there is more of it. So the temperature actually is reached faster, and the process starts sooner. And while it's forming, it's still going to start basically that process. So the temperature gets extremely hot in this case. The star actually will reach even higher temperatures, will have more, consume more at a faster rate, because now you have more and more higher temperatures. And the process involved is actually a slightly different process in terms of how the star actually is confusing hydrogen, not through necessarily the proton-proton chain, but involves something else called the CNO, because it goes through the process of making those heavier elements, carbon, nitrogen, and oxygen earlier, and the process is expedited, extremely hot. Goes through a pulsating stage, and then after that, it's going to even go through a red supergiant stage and goes into supernova. As a contrast between the low mass star, the low mass star does not actually explode, but the material is actually ejected, and that is in the form of a planetary nebula. And here, because again, when you run out of fuel in the core, run out of hydrogen, you start fusing helium, because remember, helium actually can fuse at a higher temperature. And the upper shell now, that structure that was actually the inside, now is expelled outside. So you'll have an outside layer of hydrogen, and inside the helium is fusing. Now when the helium starts to fuse, is going to form a layer that is going, the ashes actually that were formed from the fusion of the hydrogen is actually the helium itself. So now you have a helium outside, hydrogen, hydrogen, helium, and then the next element, which is carbon, and then magnesium. So there is a layers that start to form in this structure in here. And each time there is a contraction, the temperature is even higher and higher, allowing for more and more elements to fuse, until at some point you form iron. Chemical symbol for iron is Fe. Once you form iron, at that point, there is no way for the star to fuse iron to make more energy. All of the processes up to this point were able to make more energy, namely more temperature, to sustain it from further collapse. But iron does not produce more energy. It's actually what is known as an endothermic reaction, meaning it needs energy to happen, versus the others, which are exothermic reactions. I know I'm using the word from chemistry. Endo and exo are from chemistry, and the word thermic is for heat, but this is an analogy to the chemistry. It's actually endoenergetic reaction and exoenergetic reaction, meaning the processes up to this point were producing more and more energy, sustaining the star from further collapse, whereas in the case of iron, if the star wants to fuse it, it needs an excess energy, but it doesn't have that. The whole reason why it's fusing them to begin with is so that it prevents further collapse. Now, collapse is inevitable. So in this case, the core shrinks. Remember, the iron now that I have in there is made up of, its nucleus at least is made up of protons and neutrons. And you have in the outer shell, we have electrons floating all over the place. So the electron will be forced to fuse with the proton, forming a neutron. So now a neutron and neutron trying to come close from one another, basically forced with the collapse to come close from another. Meanwhile, the materials that is trying to fly inward also to the nucleus is coming at an extremely high velocity, which is at some point, it's about the quarter of the speed of light. When it hits the nucleus now, the core, that is extremely dense, made out of mainly neutrons, it bounces off of it. And now the material that is bouncing off will bounce off at extremely high speeds also, meets the material that is coming inward, and that is a sign for another problem, which is the explosion that is going to happen. You will have a supernova. So these materials, they explode, and the core will further try to collapse. If you don't have enough materials, you end up with a neutron star. So basically a bunch of neutrons clumped together. That's a neutron star. If you have more mass to start with, the neutrons cannot prevent further collapse. Remember, neutrons prevent further collapse through something called the degeneracy, but now they cannot even do that. So you end up with a black hole. So basically there is an endless, bottomless singularity where you're going to have, in this case, is a black hole. So depending on how much mass you start with, if you start with an extremely high mass, then the scenario is going to end up with a black hole. To start with only several light years, in this case, you're going to end up with a neutron star. What happened to the material that is ejected due to the explosion? First of all, it happens at extreme high temperatures, in which case now there is enough energy for even the endothermic reaction to happen, even for iron to fuse and heavier elements to form. This is where the rest of the elements in the periodic table are formed. I'm trying to look for my periodic table. It's in here. Is this the one? No, I don't know what it is. Anyway, if you look at the periodic table, iron is not really at the top level. Iron is even very, very, very. Let me try to find the some periodic table in here, or at least something I can refer to. This is from my other class, okay? So anyway, iron is 26. Its atomic mass is 26. Atomic number is 26, I'm sorry. So its atomic number is 26. Remember, there are at least in nature 92 elements, up to Z equal to 92. So this is not even 1/3 of the periodic table. So you're asking what happened to the rest of elements? How do they form? If even massive stars, at most they form iron up to this stage. Well, the answer is during the supernova stage, we think most of the elements are formed. The rest of the elements in the periodic table are formed. When the universe formed initially, all the elements that exist at all were actually hydrogen and helium and traces of lithium. For low mass stars like this ones, the most they can form is probably carbon and oxygen. This ones, they can form up to iron. So where is the rest of the periodic table? It happens in here during this brief moment of the explosion, during where these two masses basically meet, the ones that are collapsing and the ones that are bouncing off of the core. That explosion makes most of the elements in the periodic table. The reason why I'm saying that most of the elements are in the periodic table, because there is a new process that we know today. So this is a supernova. There is another process that we know today, when two neutron stars basically are spinning against one another, and then they will attract one another until they collapse, until they collide. And when they do, that's actually where most of the gold and silver and all of the other elements are formed. So if you look at the collapse of neutron stars, that is actually where, I mean, you're asking where would they go? Would we have a bigger neutron star? The answer is no. We will have actually a black hole. Okay, so that's really the plus the ejected materials in here that form in here, plus the ripples that ripple through the space. That's going to be something that we know exists, and we have detected those through the LIGO system. Anyway, this is how the evolution of a low mass star is, and this evolution of a high mass star is, and those are the two scenarios that we can end up with. Okay. So again, this is a summary of what I was saying in here in terms of the evolution, how the star goes through its life cycle. I mentioned the size of a white dwarf, and the size of the white dwarf, I said that it's of the size of about 100 times the 100th of a size of a regular star like the sun, which is the size of the Earth. Remember, the Earth radius is about 6,400 kilometers, and the sun is about 700,000 kilometers. That's about 100 times bigger. So this is actually drops down to the size of the Earth. That's a white dwarf. If you look at the neutron stars are actually about the size of a city. So it's even further collapsed. This thing collapses even further to a small object. So that's basically what it is. Neutrons, I mean, a black hole does not have any really size. I mean, a black hole is singularity. But black holes, and we will have that down the road, will have a property called the event horizon, basically, where light does not escape. So there is like kind of a physical size to it, but it's kind of a outside of the actual black hole. The actual black hole should not have any size. Anyway, So let's start from the gas. That's how both stars start. Okay, so you have gas in here for the case of low mass stars, a few light years. For the case of supermassive, for the case of big stars, it's a few light years, several light years. So it's going to contract due to the force of gravity. And at some points, the contraction will reach high temperature so that the star actually ignites and becomes a star. So at this point, it's a protostar. Up to this point, then it becomes a star, but it's going to spend its life on the main sequence star. If it's a low mass star, it's going to spend a lot of its time in there. If it's a high mass star, it's going to go through this space very fast until it reaches the red giant stage. For the case of a low mass star, it's going to have a planetary nebula that forms and is going to go and feed the rest of the interstellar space for potentially more stars to form. Not necessarily always, because if it's dispersed enough, it's not going to coalesce. It's going to just form basically intergalactic clouds. Otherwise, it could feed the next generation of stars. For the case of the massive stars, that's going to have a supernova, and that supernova also in a similar fashion is going to go and feed the next generation of stars, or if it spreads enough, probably it's not going to do that. So that's a similar scenario in this case, except the case of the high mass stars, they will be rich in heavier elements, more than iron. This ones, they will be less than iron for the low mass stars. Now, depending on the size, it could end up as a white dwarf if it's a low mass stars, or it could end up either as a neutron star or black hole, depending on how big it is to start with. Okay. This, if they're by themselves, nothing is going to happen after that. But if they're part of a binary, they could feed on the binary and then go through another explosion, another release of life, if you wish, on them. So after from they're dead, they could go back into another supernova or a hypernova in the case of the neutron-neutron interactions. And that is going to feed, again, the intergalactic space until we have the process again in this cycle. So this is basically, in a nutshell, how the stars go through this cycle. Now, in terms of the HR diagram, we have two scenarios. For low mass stars or a high mass star, they both start at protostars, extremely cold, temperatures less than 1000 Kelvin. And they start to heat up as the material starts to coalesce. And as I was saying, the process is expedited for the case of a high mass star because you have more materials to begin with. And it's slower process for the case of a low mass star. The whole process is expedited for a high mass star because you have more materials to begin with. And they end up super hot, temperatures extremely hot, and they end up with super bright stage because super bright conditions. So they are going to emit a lot of light, and they go there and process much faster until they become red giants, red supergiants, I should say. And then they explode into a supernova on the diagram. And at that point, they will end up being either a neutron star or a black hole, depending on their size. Now, for a case of a low mass stars, again, it's going to evolve from its main sequence star to a ZAMS, in this case, 0H main sequence star. And then they're going to evolve. For the case of the sun, it's somewhere in its main sequence life. Then it's going to go through a red giant. Then it's going to go through helium flashes, where it's going to go through a yellow giant. Then it's going to through a planetary nebula that's going to be ejected, and the star evolved through the HR diagram. It becomes a white dwarf. Trillions of years, billions of years after that, the white dwarf cools enough to become a black dwarf. It is very important that you guys understand that the stars do not really move in the diagram. I know when I did this before with another class way in the past, they thought that the star is actually moving around. No, it's in the same location, going through the brightness and the size and the nuclear reactions that are happening, all of it in the same location. Granted, stars are not stationary. They're moving around the galaxy from wherever they are. So in its evolution, where it's normally moving, that is how it's going to go. It's going to grow, for the case of the sun, to a point where it's going to engulf Mercury, Venus, Earth, and even potentially Mars. And then it's going to go through the planetary nebula, ejecting all of those materials. So the Earth will be no more. Probably Jupiter will be there, but then it's going to shrink back into a white dwarf. So Jupiter will be still going around the leftover, the white dwarf of the sun and the other planets also are going to be, I mean, their path probably will be slightly disturbed. So this is a very important point I want to make, because sometimes my students, at least in the past, exhibit some sort of a little bit of confusion about this one. So I want to make sure that you guys don't have that. Unit 62. Okay. Again, we're continuing with the basically it's very, I mentioned that when I was talking about the case of the big stars, that they don't really necessarily go through the proton, they go through it quickly, the proton-proton chain. Remember, proton-proton, you have basically 6 protons combining to form helium plus ejecting 2 protons. So you actually, in a count, you have 4 protons, which are the hydrogen nuclei. You add them together and you end up with a helium nucleus, which is the alpha particle, plus 2 neutrinos, plus a bunch of energy. That's basically what the proton-proton chain is. So it's protons coming together and forming helium nucleus. For the case of the supermassive stars, it's actually an actual cycle. You go through carbon, nitrogen, oxygen, carbon, and no, probably repeat it again. And in doing so, what you're actually doing, you're taking still 4 protons from the core of the star, forming in the same fashion helium and 2 neutrinos plus energy. So this diagram looks the same, except this one requires much, much higher temperatures, and that's how the high mass stars are doing it. Again, the purpose of this is to maintain that hydrostatic equilibrium. Star is bigger in this case, supermassive, and is going to collapse even more, increasing the temperature further. And that increase of the temperature will provide enough pressure to maintain it from further collapse if the star makes enough energy inside. And that's the whole purpose of this, to maintain itself from further collapse. Okay. So again, the protostar for the low mass stars is you have a weak gravity because you have less material to begin with, and so the process is extremely slow and takes a long time for the star to evolve through the process. Okay, whereas for the big star, as I was saying, you have more materials and the process starts sooner. So high mass stars are actually going through their processes a little faster. So here is the CNO cycle. So the CNO, the C stands for carbon, N stands for nitrogen, and O stands for oxygen. And I'm kind of not really happy about the fact that I don't have my periodic table in here with me to see this thing in here. Otherwise, this would be nice. You will see in the periodic table that you have the carbon, followed by nitrogen, followed by oxygen on the periodic table. So when you have a chance, and if you go to a chemistry lab or even a physics lab, look for the periodic table, and you will see the 3 of them, they are one after the other. So the lower number of this is carbon, and I like to start with the normal carbon because carbon, and here I see it carbon 12, which is the standard carbon. I see carbon 13, which is an isotope of carbon. So I'm going to start with a normal carbon in here, which is the typical carbon, okay? Because it's a cycle, you can start anywhere you like in a cycle. It doesn't matter where you start. As I said, in here, I'm going to start with carbon. So think of a carbon in here that has formed already in a supermassive star, where the temperatures are the order of much, much higher than that of the regular star. So in this case, this process is allowed. So what you have in this case, you have a bunch of protons still in the core, mainly hydrogen. Hydrogen is going to collide with the carbon. When it does, in this case, it emits energy. So gamma in here, when you see the symbol gamma, the Greek letter gamma, that means it's energy. So now energy is emitted in the form of radiation. Now, carbon is 12 nucleons, meaning you have 6 protons and 6 neutrons. Add to them another proton, 1 proton, 6. So this number becomes 7 protons, but still 6 neutrons, for a total of 13 nucleons. So 7 plus 6 is 13. But now, instead of Z being equal to 6, how it was before, now is Z equal to 7. So you have moved in the periodic table from one element, which is carbon, down to nitrogen. Nitrogen has more protons in it. But in this case, this is actually not the normal nitrogen. This is the isotope with 13. So this is not really actually stable nitrogen. So automatically, that proton that you added will split into an electron that is positively charged in a neutrino. So again, we have captured one neutrino. We have one. But we have a positron. Positrons are not something that you see on a regular basis because they are actually positively charged electrons. So this one will meet another electron and they will cancel through a process called annihilation. So they will cancel each other and you will form energy. So again, energy is produced in here from these two. So you have a bunch of energy produced in the first stage, and now we have more energy produced in here too. Well, this carbon, which is different than normal carbon, this is carbon 13. Carbon 13 now has 6 still protons, but now instead of 6 neutrons, it have 7 neutrons, because one of the new protons that was here changed to a neutron. Changed to a neutron. So now this is carbon 13. Add to it another proton. So now we have 7 neutrons. Now add to it another proton. We had 6 to begin with, plus 1, that's 7. So we have 7 electrons and 7 protons and 7 neutrons. And that, where did we get this proton? You're asking. Where we got? Where in the core? We have a bunch of hydrogen in there. So this is normal hydrogen. So in this case, plus energy that is going to be emitted. But this is nitrogen now. We're back to Z equal to 7, which is nitrogen in the periodic table. So this is normal nitrogen, nitrogen 14. Nitrogen 14 is actually stable, but in this case, there is a bunch of protons. It could capture a proton, and it would at these high temperatures, and emits again energy and changed into an oxygen. So now you have 7 neutrons, but then you captured another proton to the additional 7 protons. Now you have a total of 8 protons. 8 protons in the periodic table. Z equal to 8 is actually oxygen. But this is not the normal oxygen that you and I breathe most of the times. This is an isotope of oxygen that has only 7 neutrons. Normal hydrogen, normal oxygen is actually 8 neutrons in addition to the 8 protons. Plus energy that is emitted. So now you have this oxygen that you have. This is not a stable oxygen. It's automatically going to, one of those protons will change into a neutron. So now we're back to the number of protons, neutrons now increased by 1 because one of them changed to a proton. But now that proton is gone. So we're back down to 7 now. So this is actually Z equal to 7. Now we're back to nitrogen again. But this is an isotope of nitrogen that has 15 nucleons, namely 8 plus 7, which is 15. What happened to the proton when it decayed? Again, it formed a positron. Positron, which is a positive electron, will meet another electron and give you 2 times the energy of these 2 masses. Plus, and that's important, another neutrino. So now, if you're keeping tab of the neutrinos, we have 2 of them altogether. 1 in this stage and 1 in here. So we have 2 of them. Well, this nitrogen will meet another proton, and now something else happens. When it meets another proton, the total number of protons now will become 7 plus 1, that's 8, plus another one that is 8. I mean, the protons that neutrons doesn't change. So you take away 2 from this, you'll be left with 6. You take away 2 from this, you'll be left with 6. So you're back to the normal carbon, which is 6 and 6. But then the 2 that have gone, the 2 protons and the 2 electrons, they form helium. Helium has 4 nucleons, namely 2 protons and 2 neutrons. And that is your regular helium that forms. So what happened? This cycle is closed. So you're going to go through the cycle all again and again and again and again. Not the number of carbon will change, not the carbon of number of N13 changes, not the C13 changes, N14 doesn't change, O15 doesn't change, N15 doesn't change because you're a closed cycle. What changes in here, what matters is 1, 2, 3, 4 protons come in. So you have an H and an H and an H and an H, 4 of them. What did you get out of this? Well, this is what we got. First of all, we got helium 4. And what did we get also? We got 2 neutrinos. And what else did we get? We got energy here. We got energy here from the cancellation of the positron and the electron. We got energy here. We got energy here. We got, again, this energy, which is the annihilation of both the electron that has formed positively charged electron and the negatively charged electron that exists everywhere in the core. So you have energy in there. So you have energy that has formed everywhere, similar to how we had it in the proton-proton chain. As a matter of fact, if one looked at this one in here and didn't know that this is what's going on, they would tally and find the same number in here for the previous chemical reactor, the previous reaction that I mentioned, I think, in the previous slide here. This is identical. So the process is similar. The process is similar. Okay, but this one happens at higher temperatures than that of a low mass star. Internally, stars, basically you can divide them into 4. This is a regular sized star like our sun. This is dwarf stars, and this is a supermassive stars. For a high, the core, first of all, it's high density everywhere. Okay, so that's where the nuclear reactions are happening everywhere. Okay. For the case of a for the case of the sun, there is a region in here, a radiative region, region, because there is not basically the photons are not absorbed by the stellar gas. They're still too hot in this case. I mean, it goes straight through, but then in here they're absorbed. And this, the only way for it to transmit energy is through the convection. The convection zone is very far. In other words, the gas of this in here does not mix well. So whenever it runs out of fuel in the core, that's it, no more. For the case of the supermassive stars in here, there is a lot of material in this case. Even in here, the density is super high outside of the core. This is where the nuclear reaction is happening. So in this case, there is not enough material. I mean, the material is too much for the radiative zone to happen. So in this case, the process through which to get rid of energy, the only way to do it is actually through convection. And that will actually enable more and more materials to go in. So that's going to even make the star go even crazier in terms of temperature. And that's why you have all of these processes I was describing earlier, in terms of higher and higher masses and more temperatures and things like that. For the case of a low mass star, in this case, you don't have enough materials in this case for it to have actually a radiative zone. So actually, low mass stars, they mix most of their materials more, and they consume it at a lower rate. So that allows them to even live longer because you have more material infused and circulated around to be fused further. And the whole process is slower, which takes even longer. So it runs dimmer compared to the other stars, and it takes a long, long time. So that's basically, this is, for example, for the case of a brown dwarf, okay? So that's basically, in a nutshell, how the stars go through. I mentioned the ZEM several times in here. And that's basically on the how long it takes for a star to go through its life cycle. The less massive stars live longer, from about 10 billion years for the case of the sun, down to about only a few million years for the case of the supermassive stars. Because again, as I was saying, you have more materials, yes, but you're consuming it at an extremely high rate. As a matter of fact, the age of a star is inversely proportional to the luminosity, because you have more luminous materials in here. And its mass, yes, the more mass, you're more luminous, but then you're inversely proportional to the luminosity. times 10 billion years. That's the age of the sun. Granted, the mass of the star is here is in terms of the mass of the sun, how many suns you're looking at, and the luminosity is in terms of that of the luminosity of the sun. There was a formula that we have seen earlier before, that the luminosity is actually proportional to the square root of the 7th power of the mass, basically. Or I think we wrote it symbolically as 3.5. I mean, the mass to the power 3.5. If you plug in this expression in here, the time that the star lives is actually inversely proportional to the mass, because it's going to be slightly, or the square root of the mass to the power 5. 5 over 2 is 2.5. Times, of course, 10 billion years. So this is how, in other words, more massive stars, they live shorter than low massive stars. Even lower than that, they even live a lot longer than the medium-sized stars. So this is in a nutshell how this unit is structured. This is not in lieu for you guys to go and read the units. So you're still required to go and read the units. Let me share with you briefly the last unit that we're supposed to cover today. That is unit 63. Okay. Again, in terms of structural changes, which is also another important process. So again, this is something that we talked about earlier several times, the internal balance and how the stars evolve and so on and so forth. In terms of a red giant, in terms of a supermassive star, again, as it shrinks, it's going to fuse more of the shell in this case. And as it does, that's going to increase the temperature, which expels more of the materials outside. So this, we talked about it earlier. And the evolution of all of the stars, whether it's a low mass star or high mass star, for the most part, they're going to be in the either the red giant location or the supergiant location, at least in the red color still. Okay. Helium does not usually fuse. I mean, if you think that the process was difficult for hydrogen to fuse, it's going to be twice as hard for helium to be fused, because of the fact that you're dealing with more masses in here, with more charges, I'm sorry. Remember, the repulsion of the hydrogen and the hydrogen is to the fact that both of them are positively charged, and the force that is responsible for their repulsion is proportional to the square, to the product of the charges divided by the distance. Obviously, if they are far away, they don't repel as much if they are close. But if they are close, then you cannot really fuse them. The only way to do that is to force them to fuse. When they do, they form this, the two hydrogens. One of them has to flip to become a neutron, and that reaction will result in a positron plus a neutrino. If they're close enough, if the temperature is around 10 million Kelvin. However, even at those temperatures, it's not high enough to force two helium atoms to fuse. The reason why that is because now each one comes with the two positive charges. So the force now is 4 times bigger, because 2 times 4, 2 is, this is E squared divided by R, by the way, R squared. So it's 4 times bigger. So you really need more temperatures to fuse helium, to force it to come close enough so that you can form beryllium in this case, which can capture another hydrogen, another helium, and form carbon. So for this one to happen, for the carbon to be made, you really need to have extreme high temperatures. That's the bottom line, okay? So 10 million Kelvin is not going to do it. For the case of the sun, it's about 15 million Kelvin. That's not high enough to form the heavier elements, at least at this point. Down the road, it's going to be hot enough to do it. Again, I mentioned several times the electron degeneracy, and this is what prevents the white dwarf from further collapse. And that's basically as if, I mentioned it several times actually, that 2 electrons cannot occupy the same energy level. They cannot be in the same state, basically, the same location. So they will prevent further collapse of the star, because you don't really have a lot of materials. For the case of a neutron star, you have enough materials to even bring those protons and electrons close enough so that they actually fuse and they become neutrons, okay? I mentioned the helium, basically reactions in the core of the star, and that's basically in a nutshell this units. Hopefully you guys will go through the readings. I will make another video for you guys. I know this is the live session, but I will make the videos for next few units, and I'll post them hopefully by Wednesday. If you have any questions, please let me know. Again, please take care of the review. The review is on Canvas. Please also take care of the assignments that are still due. You have quizzes. And for those in the lab, I will see you tomorrow afternoon or Thursday. Thank you. I'm going to stop the recording now.